Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL online course on structural systems in architecture. Today we will discuss the lecture 14, and it is on the module number 3, week 3. Structural mechanics is the name of the module, and lecture 14 is the title is having a title shear stress in beams. So, the concept we will be covering in this particular lecture is we will introduce the shear stress, and we will then going to define the shear stress in a beam section and how it can be calculated and how it can be measured, that we will see. And then we will see also the shear stress distribution profile in beam section and some numerical problems. The learning objective for this course is we will derive the expression of the shear stress in the beam sections, which is one of the essential part of this particular lecture. We have to initially cover it, and after we know the shear stress, the expression of a beam section, we will explain the shear stress distribution in beam in different type of beam section. We will see that in different sections how it will going to vary, or how whether it will going to stay as it is or not. And we will have to formulate, we will have to apply the shear stress formulation to evaluate the shear stress for a given beam. So, let us start with the shear stress. As you all know, the shear stress is a stress which will be applied by the shear force, and the shear force is nothing but a force which is applied in a particular junction of the planes or the layers in between the two layers or so. So, suppose here I have shown in the PowerPoint in the presentation, I have shown a two plates, steel or maybe wooden plates. It is actually joined by a bolt or a rivet or maybe some kind of a key, and this is a lap joint. This is called a lap joint, and if you just pull both the things in a two opposite equally and two opposite direction, what will going to happen? Initially it may stay for quite a sometimes, because if you do not have enormous amount of force, but if it is increased too much and if it is further more the capacity of this rivet or whatever, it will going to break. Now, why it will going to break? Because in this particular cross sections of this two plate, there is a shear force developed, and the shear force is applied on that particular the section of the bolt, and which is much higher than its capacity, shear stress capacity, and then it will going to fail. There is a shear failure, and there is a this kind of the smashing kind of a failure. So, we can say that the shear stress is actually, it is not axial. Axial stress are perpendicular to the axis of the body, okay, but the shear stress is something like which is along with some planes. Now, if I take a beam, and this beam is supported by two the support in the two ends, and of course, this beam is not too, it is I have drawn a too fat beam, but it is not supposed to, I am just zooming the central portion, and if I just load on this particular beam with some kind of a loading, so shear stress is developed. Of course, the bending stress is also developed. We have seen in the last 3 lectures how the bending stress is developing and how the bending stress in the different sections can be calculated, and the triangular distributions and all. But the shear force is a transverse kind of a shear force will be applied in the beam sections. So, each and every layer, if I imagine that this total depth of the beam is having 100 such layers. So, each the first layer and the second layer, there is a kind of a transverse force will be applied to each other. There is a second layer to the third layer, there is another kind of the shear forces will be applied to each other. So, those each and every layer, the shear stress the concentration of the shear stress or the magnitude of the shear stress may vary, may not vary, that we will see afterwards, but there is a kind of a shear formation or the shear stress formation. So, due to this shear stress, if it is very less, fine, no problem, the beam will keep as it is, but if it is really large, if you just put little bit extra amount of loading or huge amount of loading, then first what will going to happen, there will be some kind of a flexure cracks will appear in the mid section, because this is a simply supported kind of a beam. The flexure means bending crack or the crack that that's developed due to the bending stress. And as it is understood that this is a simply supported beam and it is going to have a sagging kind of a moment, the tension will create will occur in the bottommost fibers, and there is a crack will develop, and this crack is a perpendicular crack. It is start from the below the bottommost fiber, and that it will try to go towards the neutral axis or the center of the beam. But afterwards it may also generate some kind of crack which is other way inclined, and those cracks are shear crack. You will see the cracks which will be generated, and that will be in a 45-degree orientation, and that will be the shear crack. And why this is 45-degree crack and why that is a shear crack, we will understand maybe little later. So, now let us go to the stress distribution, how to measure that particular stress and how I can say that there is a shear stress develop. So, this is a kind of a beam again. So, and this particular beam is loaded with these two concentrated load. So, definitely this particular beam will have some, I mean if you have some other loading also it is possible. So, it will have some kind of bending moment diagram or something like this. So, this is a bending moment. So, if this is a bending moment diagram, so I have taken two such sections in the beam, one suppose AC and one is BD. So, definitely is these two sections are little apart. So, the bending moment at the AC maybe it is something m, and in the BD it is something m plus some extra something some x, suppose some extra or maybe little less or something like that. It may not be equal. So, if it is not equal, so there is a different kind of a stress distribution and different type of the forces will going to apply. And let us see how these two sections AC and the BD will have the stress distribution. I am talking about the bending stress distribution that we have already we have discussed in the last few classes. So, I will have say that the lower bending moment will be in the section AC and the higher bending moment will be in the section BD. Eventually it is right, because as and when you will go to the center of the beam, the bending moment gradually going to increase, and maybe in the central portion the bending moment is maximum. So, as AC is little bit towards the support, I can say that it is a little bit less amount of bending moment, and whereas in the BD which is near to the mid span, which will have some high amount of bending moment. So, again I have make a zoom view of AC and BD. So, AC will have and BC will have the bending stresses. So, as I have assumed that the AC is having less amount of bending moment, so the bending stress compressive and the tensile will be smaller, whereas the BD, the compressive and the tensile bending stress will be higher. So, this is higher and this is smaller. So, in any layer if you just compare the layer, if you compare any layer, it is higher and it is smaller, the AC will be smaller and the BD will be higher. So, suppose if I take a layer which is just above the neutral axis, some height, and just below, maybe some below the from the topmost fiber, the green color layer. So, I can say that in AC, suppose if it is sigma is the stress, that is this is the sigma. So, the other side BD, in the same layer, that layer will experience some extra, some delta sigma extra. Why? Because BD will have the higher amount of bending moment. So, if this is so, I can logically say that yes, if this is so, then how much is the force? So, force is nothing but the stress into the area. Let us suppose this particular thin line or thin layer which is the green layer I have drawn over here, it is having the area of small dA, that is the elementary area dA. So, the force will be, here it is the sigma into dA, and whereas the force, the additional force, the little extra force delta dF will be sigma plus delta, there will be a sigma and dA. Okay. So, there will be some additional amount of force. So, now I transfer this sigma to moment, as I know that the m by I, that is the famous formula, bending formula of m by I equal to sigma by y. So, sigma is equal to your m by I into y. I have just replaced the sigma by virtue of this m by y or so. Here also I have replaced, but here m is little bit extra moment or the little higher moment. So, I understand that this particular green layer will have some differential amount of stress. So, differential amount of force, both the forces are not equal. This force here in AC and this force here in BC is not going to equal. There is the unbalanced force. So, unbalanced force, how I can find out? I can find out from this minus this. Okay. So, this whole, if I take minus from the second one to the first one, I can find that this is the amount of the unbalanced force is applied in a small area dA, which is about y from the NA. Please remember that this is these two are very important. Only in this particular small dA area there is a unbalanced force is occurring, which is delta m by I into y into dA. This is for the small area. So, that is why if you just push a particular beam, you will see that if there is no adhesive in these two logs or these two pieces of the wooden piece or anything, maybe you can take two scale and just put some kind of a load, there will be some kind of a slippage. Why slippage? This particular unbalanced force will be there in between them and they will try to slip with each other. So, that is the shear force. So, I can sense some kind of an unbalanced force, which is a sense of a shear force. So, I have again take that particular AC and BD in a zoom view, and let us assume that the distance between this AC and BD is also very small, and that is del x. Okay. And this is the sectional depth of this particular BD section depth. So, the small area that I have marked over here, which is x from the neutral axis. So, I have marked both the figure, both the views on that. Now, I have an unbalanced force in that particular area, on this particular area dA. But how much is the unbalanced force in this total region from y to y top? This particular region is the y to y top. I am very interested to find out that how much is this particular force, unbalanced force in that. So, unbalanced force will be that, see, it will be the sum of that unbalanced force in dA from y to y top. Mathematically I can write like that, and I can redistribute this particular total unbalanced force, because del m and I does not have anything with the y and a. So, I can take it out. So, I found this particular under summation sign is summation y to y top, the dA and the y. That means it is going to be the area of this particular area that it is above this particular y, this area, and the CG of this area to the neutral axis. So, that is called the first moment of area above the line, above the depth y, above the line depth y. So, I can find out the total unbalanced force now, not in dA, but the area which is above that particular y distance, a selected portion, selected layer y distance or so. So, this particular unbalanced force has to be supported by thing, because this cannot be, for the equilibrium you need kind of a support. So, that is the inherent shear stress developed by the particular body, and that particular shear stress will be acted like this, the opposite direction. So, that is the force. So, if I want to find out the shear stress, I have to divide that particular force by the area. The contact area of that particular the beam is B into dx. Why dx? Dx I understand, because this is the depth or this is the length, and B is the, this is your B, this is your B. So, the area of this the area of this area is actually B into dx. It is the lower portion I am talking about. So, if I divide that, the unbalanced force, divide that B into dx, I can find out the shear stress. But this is the expression of the shear stress, where the first term is the differentiation of the moment against x, the length, 1 upon I b into A y bar. Further, I may write the same, and I may say that this dm by dx, that is the rate of change of bending moment, is nothing but shear force. If you remember, in the second week we have studied that one in one of our lecture, that the differentiation of the bending moment is nothing but the shear force. So, finally, I got the equation. So, I replace this dm dx by F shear force, nothing but F, I, B, A and Y, everything is explained here. Q is the shear stress, F is the shear force, I is the bending moment of inertia of the particular section, F is the shear force at the particular section, B is the width of the particular section at that particular location, A is the area of the portion of the sections above the specific location. I am interested to find out the shear stress at this specific location, right, at a distance y from the neutral axis, and the y is the distance from the CG area to the neutral axis areas or so. So, now the stress distribution profile is look like this of a I have to find out the stress distribution profile of a rectangular beam, which is having the D into B is the cross section. So, I have found out the at a particular distance y, what is the expression of the shear stress. So, this equation I have taken, F remain F, I and B doesn't no change. Now, A and Y bar I have computed. What is A? A is the area of the sections above the location. So, that means is green area. The green area is nothing but the B into this depth is D by 2 minus Y. So, I have put it over here. Now, how much is the Y bar? Y bar is the center, the CG of that green from the neutral axis. So, this is I have computed y plus half of D by 2 minus Y. So, this is this much. So, I have put it like that. Now, I have again multiplied, and finally, I found out this is the expression of the shear stress distribution. So, I have already explained that one. These two are the arrows, and this the shear force distribution is going with this particular formula. F and this B going to cancel. So, F by 2 I and D square by 4 into Y square. So, this is the equation of a parabola. So, shear stress distribution in rectangular geometrical rectangular beam is parabolic. Now, see what are the how it is going to define. The top layer and the bottom layer, the shear force has to be 0, y 0. In this equation, if I say top layer, the y equal to, what is the value of y? Y equal to, the y is what? Y is the distance from the neutral axis, the layer. So, layer is the topmost layer. So, it is going to be D by 2. So, put y equal to D by 2. So, it is going to cancel. And in the bottom layer it is minus D by 2. Again, if you put minus D by 2, minus D by 2 square is minus D square by 4, cancel. So, these two are 0. Now, I am interested to find out at the center of the neutral axis. Neutral axis, the y value is 0. So, I put y value is 0, and now I recalculated, and I found out that the Q is 1.5 into F into BD. So, that is the green point, and the distribution of this thing, will it be rectangular or straight line? No, it won't be. It will be a parabolic distribution, because the equation is a parabolic equation, equation of a parabola. So, if you now see the Q max, this is the maximum value, which is your 1.5 times Q into B into D, which is this actually. This is the maximum shear stress in this particular beam at the neutral axis, which is 1.5 times the Q average, because F by BD is what? F is the shear force and BD is the area of the beam, which is the average shear force in the beam, which is 1.5 times the average. So, maximum shear force is 1.5 times 50% average in case of rectangular beam. So, if you design a beam with the average shear force, taking into consideration, then the beam will fail, because the actual it will come 1.5 times higher than the 1.5 times the Q average in the central axis or the neutral axis, and definitely in that particular central portion there will be crack and all those will be the form. So, I have also calculated for the circular section. So, the stress distribution is like this, and if this is the stress distribution, top layer and the bottom layer will be 0, and also I have found out the neutral axis layer, which is y equal to 0. Just put the value of y equal to 0 here, and I got the maximum stresses and all. And I also found out that the maximum stress for the stress for the circular section is 1.33 times, 33% higher than the average. So, all the cases it is higher than the Q average, but it is not same, it is 1.5 times for the same rectangular case and 1.33 times for the circular case. So, I have one small problem. So, I have a low beam which this is not a problem. So, in the near support, if you see, the SFD are higher and the BMD is low. So, your distribution diagram will be like this. This is your bending stress distribution, sigma compression and the sigma tension, which will be smaller, and this is the Q. But if you see the central portion where the mid span, where the shear is low but the bending moment is high, so Q will be low and this will be very, very high. So, that we have to note. So, I have taken a small problem. So, it is the beam, and I have found out the shear force at the support and also shear force at the 2 meter from the support. So, I have calculated the shear force 100 over here and 50 over here, and I found out with this particular, because this is a rectangular section I have already mentioned. So, from there I found out as and when you go towards the mid span, your shear force will going to decrease. So, it was 1.11 in the near the support and 0.55, almost half. Of course, it has to be in the near the 2 meter from the support also. It is going linearly decreasing. It is a cantilever beam. So, SFD and BMD diagram is like this. It is also the same type of the section. So, I have found out the F max is will be the in the support. So, this will be W into L. So, I have found out the shear stress, that is the maximum shear stress is 0.8 Newton per mm square, and the BMD is WL square by 2. So, 120 kilonewton, and the M max, sigma max will be that M by Z gives me 14.22 Newton per mm square. Okay. So, both will be applicable in the near to the support. So, for a T beam or those kind of a beam which is a flange kind of a beam, it will be very interesting to see the how the shear stress diagram is there. So, center of gravity I found out it is 83 above the bottommost layer. Moment of inertia is also found out. Now, we has to see that the top and bottommost layer it has to be 0, as we understand. So, the topmost layer it is 0 because the A is 0. What is A? A is the area above the selected section. So, in the topmost point in this it is selected section, above the section, how much is the area? Area is 0, no area, because this is the topmost point. So, as A equal to 0, this is equal to 0, whereas in the bottommost section it is 0 because y equal to 0. Y equal to 0 is the CG of this area is 83 and it is lie on the 83 itself. So, the difference between the CG NA and the CG of the area is 0. So, that is why y equal to 0 and this is 0. Now, let us see what will happen in the middle. But before we go to the middle, we have to see this particular junction area. So, you first let us find out what will be the in junction area, how the stress will be. Now, assume a line just above the junction, not exactly at the junction, maybe a 5.01 millimeter above the junction. So, first I have found out here, you see the A and Y bar. A is 150 into 10 because why? This is a junction. So, the area of this is equal to your 150 into 10, right? And Y bar is 22 mm. Why? Because this is your 27 and this is the CG of this thing will be just 5 below. So, 27 minus 5 will be your 22, will be this much CG Y bar. Okay. So, the Y bar is like that. Now, I put every values over here in this formula, A 1500 and Y bar as 22 and your the F value, and this is your I value from the previous table, and this is the B is 150. Why? The width of the section at this particular area is 150, just a millimeter above the junction. So, I got 8.27 is the distribution, stress distribution. So, that is this 8.27 over here, and this is parabolic distribution. But what happens if you just go little below that millimeter, now below in the neck, in the wave, everything remains same. This remains same, this y bar remains same, the F remains same, the I remains same, only change will be from 150 to 10. Why 10? Now the thickness of this B value, thickness will be now, as it is in the neck, in the wave, it is just 10, just millimeters. So, the Q value will be 124, almost 124. So, it will be jump in that particular point, it will be, or particular layer, it will jump because of the neck formation or this wave. And finally, at the CG, that is 83 above or 27 below, I have computed the AY bar, that is first area is 1500 into 22 is that the CG, 1500 is the area, and second area, that this neck area or the wave area is 170, because this is 17 into 10, 170, and the half of 17 is 8.5 is, so total AY bar is 3,445. And the B value is your here 10. So, I can now easily calculate the Fy bar, 100 is the F, this is the I, B value is 10, and this is your AY bar. So, this is 129, which is the highest. So, that will be the shear force distribution diagram. So, it starts from 0, it goes here, it's jump like this, goes here highest, and then again go back and 0. So, this will be the, any neck formation will increase your value, and this increment will be how much? It will be 15 times here. Why 15 times increment? Because this neck is decreasing by 15 times. Only change, if you see in the earlier slide, is 150 to 10. So, definitely this will be increased by 15 times. So, this is the another problem I have explained here with the I section, symmetrical I section. 80 by 15 is the flange, and 170 by 10 is the wave. So, I values, and F is this is 100 is the shear stress value, shear force value, sorry, and definitely this will be at the CG will be at the center, 100 and 100, because total depth is 200, and I value also I have calculated. So, I can see that it will start from 0, then it will be top and bottom will be 0, then it will be have some kind of a neck, and there will be jump, and I know this jump will be 8 times. If I can find out this will be 8 times. Why 8 times? See here, this B is at this particular point, it is your 80, the B is your 80, but here it is your B is your 10. So, everything will remain same. If you just see that earlier example, only the 80 will change to 10. So, the jump will be 8 times, and finally, it will be have some maximum at the CG axis. So, I have computed at the junction, I have found out the flange and this AY bar. 80 into 15 is the area of this, and the Y bar is 92.5. Why 92.5? This is 100, and this is 7.5. The half of the 15, this is your 7.5. So, this is your the CG of this to the neutral axis is your 92.5. So, that is given. So, this is your AY bar, and I have computed for this particular point, that is your 5 point by divided by 80. Please remember, all I value, sorry, F value, I value remains same, 1110000 is the AY bar. So, 5.62 is the Q value at this particular point, right, and the same will be in same layer. Just if you just go below, the AY bar remains same, only this 80 now become 10, because the neck, at the neck the B become 10. So, this is your 45. So, almost 8 times increment 45. And finally, I also found out the AY bar at the centermost or the CG point. So, this the area, and this is the area of the neck or the wave area, and this is the flange area. So, total A y bar is this, and finally, it is 59.6. Okay. So, from this point of view, we can actually calculate this way, you can calculate the shear stress distribution in the beam sections, various beam sections. So, I have taken the reference of those books, and in the conclusion I must say that the transverse shear force is developed in the beam due to the external loading. The shear stress distribution is mostly parabolic over the depth of the beam section. The top and bottom layers, the shear stress is 0, while in the central wave portion it is maximum. So, I have given 2 homework for you. This homework, if you just see that, you can try this particular homework, that this is a I section is given to you, and you have to find out the proportion of the flange and wave resist the bending moment and the shear force. How much bending moment the flange can take and how much proportion is proportion. You cannot find out the exact value because F and the M is not given to you. So, the proportion of how much percentage is taken by the flange, how much percentage bending moment is taken by the wave. Similarly, how much percentage will taken shear force is taken by the wave, and how much will be the flange. So, mostly if you see the bending moment, the flange will take maybe 85% higher, and the wave will take rest 15% mostly. This is not the correct answer, but mostly it will be take higher, bending moment definitely will be high at the this these two portions. So, the contribution of flange will be higher, whereas for the shear force, if you see the shear force you will see the flange will be taken maybe around 10% or so, or 15%, the wave will take rest 90% or something like that, because the shear distribution is something like this, right. So, the flange portion is very small, the wave portion is very high. Here the flange portion is very high, this is the moment and this is the shear and this is less. So, this will be the typical distribution. So, you have to mathematically compute and find out the what is the exact value. It may not be exactly 85 or 15% or so. You can, another thing, you can draw the shear stress distribution for this cross section, symmetrical cross sections. The shear force is 100 kilonewton. Please do these two particular problem. Try to practice. Thank you very much.